Hello guys, welcome back to my channel Gamma Die Gamma. And in this video I would like to do another interesting integral. So let's get started. Okay, so the problems I, integral from 0 to infinity, x times the sine of pi x divided by beta squared minus x squared dx. Okay, so before getting started with our complex analysis rituals, I would like to point out one thing. The poles are at plus and minus beta, which means that the poles lie on the real axis. So when we're designing a contour, we would ideally have to skip over them like that, and then the contour integral of the function that we would define would be 0, because apart from those guys there are no poles inside this contour. But now the issue is like this. I mean, this works fine, but if we consider the contour along the imaginary axis, this contour had a base on the real axis. If we consider contour with base on the imaginary axis like this, then it's a little different, because then we automatically have this pole of beta inside, and then the answer is not 0. So which one do we choose? Well, in the reality we choose the one which does not give the triviality. In the case of the disappearing integral, if you remember that video, I think I was like 2 videos ago, in that video we used this contour and showed that the integral disappeared to 0. But the catch is, if you use this kind of contour with with some pole inside the contour, again it goes to 0, because there was a sine. The sine of 2 pi would have given you 0 in that video. So instead of, now we can't, I mean, using this contour is going to give us some trivial answer, which is not the what we expect, because of, you know, what Wolfram alpha yields. We could, option 1, use this contour. Option 2 is what I'm going to do in this video. So this is just what's at stake. Okay, so after learning what's at stake, I'm going to present you with option number 2. Option number 2 is using the Laplace transform property. So we can take the inverse Laplace transform of this guy, x over beta squared minus x squared, and the Laplace transform of sine of pi x. And this is possible because the limits of integration are from 0 to infinity. Well, you would like to multiply by 2 negatives, because one negative can be taken inside the inverse Laplace, and we get x over x squared minus beta squared, and the Laplace of sine of pi x dx. And the negative was useful because if you remember last video about the Laplace transform of hyperbolic trigonometric functions, this is exactly hyperbolic cosine of bx, and the Laplace of this is pi divided by x squared plus pi squared dx. And now, using hyperbolic cosine, we don't need a vertical contour like option 1. We can work with a horizontal contour too. So now when we want to generalize stuff for complex analysis, we can generalize in this way. e raised to z beta divided by z squared plus pi squared, and this is what we'll have to perform a contour integration on for. But what's the contour? Okay, so this is going to be our contour. I'm just going to label a few things, and we have one pole inside the contour, the pole at z equals I pi. So that's nice, because now there is at least some pole inside, and therefore the residue, sum of residues won't be 0. And then we perform contour integration. So first you go from negative r to 0, f of z dz, then go from 0 to r, f of z dz, then go around gamma, f of z dz. On this first path, z is equal to negative x. So I'm just gonna skip some steps. If integral from 0 to r, and then we end up with e raised to negative beta x divided by x squared plus pi squared dx, plus on this guy z is equal to x, integral from 0 to r, e raised to beta x divided by x squared plus pi squared dx, plus integral over gamma f of z dz. Okay, what we can do is we can just like club these terms and multiply and divide by 1/2, because e raised to bx plus e raised to negative bx divided by 2 times 1 over x squared plus pi squared dx is going to simplify, because now this guy is just going to be 2 times, we have the hyperbolic cosine of bx divided by x squared plus pi squared dx plus integral over gamma f of z dz. And before taking the limit as r goes to infinity, I would just like to look at integral over gamma using Jordan's lemma and a little more delicate treatment, because you're going to see the statement or the proof of showing that this is 0 is going to be a little different now. So see you on a fresh page. So, but you see the basic integrand structure is pretty much what we required. So I've written the basic property of inequality of the modulus of an integral. Now I can just substitute f of z in. So integral over gamma f of z is e raised to beta z over z squared plus pi squared mod dz. And now let's parameterize, and we have to go from 0 to pi. But this time we will parameterize in such a way that z will equal I times r times e to the I theta, not r e to the I theta. We have this I factor, but the upper and lower bound of theta will change, because at the start point z is equal to r. So let's see what theta will be at the start point, the theta initial. E raised to I theta is negative I. Negative I is e raised to negative I pi over 2. You can check with Euler's formula, which means theta at the start point is pi over 2. And fine, at the end point at negative r, let's see what are we gonna get. I is e raised to I pi over 2, which means that theta is pi over 2. So our theta for this parameterization is going from negative pi over 2 to pi over 2. and we're gonna have to deal with this when we parameterize. So when we parameterize everything, integral from negative pi over 2 to pi over 2 e raised to I beta r e to the I theta over I r e raised to I theta, but the whole thing squared, plus pi squared, everything under modulus, and dz is going to be I times I, which is negative 1 r e to the I theta d theta. Now we can do some simplifications here. We can expand the numerator as e raised to I beta r cosine theta e raised to negative beta r sine theta r d theta over r squared minus pi squared. I'm using reverse triangle inequality in the denominator. This guy will become 1 because it's the mod of e raised to I times something. Now the issue is, on this interval there is the sign has a split personality, because from negative pi over 2 to 0, which is essentially the fourth quadrant, this quadrant, sign is negative, and then 0 to pi over 2 it's positive. And if you remember Jordan's inequality, that sine theta was greater than or equal to 2 theta over pi, that was only valid on 0 pi over 2 in the first quadrant, and we are in the fourth quadrant here, so this won't hold true. But what we can do is we can still split this up to 0 to pi over 2 e raised to negative beta r sine theta over r squared minus pi squared r d theta plus integral from negative pi over 2 to 0 of r e to the negative beta r sine theta over r squared minus pi squared d theta. Well, the first guy you don't need to worry about, because we can simply use Jordan's inequality and then directly Jordan's lemma to just end up with pi over beta times r over r squared minus pi. So I'm directly using Jordan's lemma. I'm not showing I'm not showing this substitution, like sine theta is greater than 2 theta over pi, then negative sine theta is less than negative 2 theta over pi. I'm not showing all of that. But on this second guy we need to do a little more work, because this Jordan's inequality doesn't hold true. So for that we need to explore the graphs of sine theta on this interval, negative pi over 2 to 0, or if you want to think about it that way, 3 pi over 2 instead of negative pi over 2. If you want to call it 3 pi over 2, it's fine. Then this will become 3 pi over 2 to 2 pi. Even that's fine because sine is periodic. So let's look at the graph. Okay, so I have in front of me the sine of the graph of sine of x, and let's just write those inequality quantities. 2x over pi, and you can clearly see that from 0 to pi over 2 sine of x is greater than 2x over pi. This was one of the characters in Jordan's inequality. And x, because you can say that x is greater than or equal to sine of x at from 0 to pi over 2. Fine. How's that helpful? Now let's look at the area we are interested in. So let me just mark that. So this area between the purple line and the black line is what we're interested in, and sine is obviously negative here. So can we get quantities like these, like 2x over pi or even x? Well, let's try 2x over pi. Let's try 2x over pi. but instead of x this time, let's just shift it by 2 pi. Whoa, okay, cool. We got something that's greater than sine of x on this interval, but that's not gonna do. Let's try doing the similar thing with an x. Okay, this blue line is clearly less than sine, and this might work because we want something that is lesser than sine on that interval. So I think this is going to work. Let's use this x minus 2 pi. Okay, so we learned from our graphical expedition that sine theta is greater than or equal to theta minus 2 pi on this interval of 3 pi over 2 to 2 pi. And if we take a negative, the inequality sign is basically flipped. So I'm going to do exactly that over here. R times e raised to negative beta r. Actually, we don't need this because we took that into consideration. 2 pi minus theta over r squared minus pi squared d theta. And we're almost done. We're gonna resolve this. If you want to change these back to negative pi over 2 and 0, you can do that, because r over r squared minus pi squared will come out. E raised to 2 beta r pi won't do anything. E raised to negative beta r theta d theta is what we'll be interested in. And then if you just evaluate everything finally, you're gonna get like a really simple expression over here. You're gonna have a negative r over r squared minus pi squared beta r actually, and e raised to 2 beta r pi e raised to negative br theta from negative pi over 2 to 0. But whatever this is, I'm not going to evaluate it. If you take the limit everywhere as r goes to infinity, this will just go to 0 because the denominator is always going to be larger. And that's precisely what's making everything go to 0. That's why this is 0. Okay, so we know one thing. If we take the limit as r goes to infinity on both sides, this will go to 0. And our contour integral just becomes 2 times integral from 0 to infinity hyperbolic cosine of beta x over x squared plus pi squared dx. And that's precisely, let's see, negative I over pi. Fine, if we simplified it. Now for the residue theorem part. Okay, so the only pole is at I pi, and this pole is probably a very trivial one from our experience. So to calculate poles, we have contour integral f of z dz 2 pi I times sum of residues. So 2 pi I, this is just one pole, so one residue. Limit as z goes to I pi, z minus I pi, e raised to beta z over z squared plus pi squared. One of the factors is going to cancel out, so we have 2 pi I, limit as z goes to I pi, e raised to beta z over z plus I pi. I pi plus I pi is 2 I pi, and e raised to I beta pi. This cancels out. So our contour integral is just I beta pi. Now our contour integral was negative 2I over pi, which means that I is negative pi over 2 times e raised to I beta pi. Now the best thing is e raised to I pi is negative 1. If you raise that to beta power, it's going to become negative 1 to the beta. So I is negative pi over 2 times negative 1 to the beta, or pi over 2 times negative 1 raised to beta plus 1. That's why when beta is odd, I is going to be pi over 2. When beta is even, I is going to be negative pi over 2. But when beta is something else, like some fraction or some other real number, then we have e raised to I beta pi, or we can just use Euler's formula, cosine theta plus I sine theta, which in this case will be cosine of beta pi plus I sine of beta pi, and then we can evaluate that. So if you think about it, it's a really nice formula we have. And the thing is, we can even generalize this. Instead of having sine of pi x that we originally did, we had this originally. Instead of having pi, we can have alpha, and then instead of when we won't have a pi in the numerator, and then the contour will slightly change. Rather, the residue will slightly change, not the contour. But you can do that. I mean, it's not hard. So I hope you like this video, guys. Please like, share, and subscribe to my channel, guys. Recommend my channel to your friends in the math community. In the meantime, stay home, stay safe, keep doing math, and peace out. Stay tuned for more content.